I'm Dr.S. Rama, Assistant Professor, Department of Physics, Joseph College of Engineering, Chennai. So today we are going to discuss the topic career concentration in intrinsic semiconductor. So before we are going to see the exact topic, first we need to see what is meant by semiconductor. So in today modern electronics, every material which is based on a semiconductor. So what are the semiconductors? Semiconductor is a solid material, right? And also it has a characteristics that material that possesses electric connectivity in between that of a conductor and an insulator. And also the semiconductor acts as an insulator at absolute zero Kelvin and becomes a conductor as temperature increases. So next we are going to see about the conductivity of a conductor, insulator, and semiconductor. So in conductor, we have a conductivity which is high 10 power 7 Siemens per meter. In semiconductors, it should be a variable 10 power minus 4 to 10 power 4 Siemens per meter. In insulators, it's a very low 10 Siemens per meter, less than 10 Siemens per meter. And the very general example for semiconductor material is silicon with germanium. So it belongs to group 4 elements with 4 valence electron. So these 4 valence electron has the 4 nearest neighboring atom. So with that 4 nearest element, it can be formed polarly bond. So this creates a stable structure. This is the basis for all semiconductor properties. So when we concentrate the temperature and conductivity, so it has a negative temperature coefficient. So that is unlike metals, semiconductor resistance decreases as temperature rises due to thermal liberation of electrons. So with the increase in temperature, it has a thermal, it has an electrical conductivity is more for the case of semiconductor. So generally, we have according to the types of semiconductor, we can have two types. Generally, we can call it as a intrinsic and extrinsic semiconductor. So intrinsic semiconductor is a pure form of a semiconductor, and extrinsic semiconductor is we can be adding some doping element to a semiconductor, so it will form extrinsic semiconductor. It is not in a purest form. Okay, so how to create an extrinsic semiconductor? By doping an element with that pure form of semiconducting material. So what is meant by doping? Doping is the intentional addition of specific impurity atoms, that is we can call it as a dopants, to a pure semiconductor to modify its electrical behavior. So why we need to go for doping is nothing but, so according to the case for this intrinsic semiconductor, it is a pure form of semiconductor. So in that semiconducting material, we can have an equal number of electrons and holes is present. So we can't able to create an electrical conductivity with that equal in number of electrons and holes. So the electrical conductivity is basically low for the case of intrinsic semiconductor. So in order to increase its electrical behavior of electrical conductivity, we can go for a doping process. So the doping increases the conductivity by several orders of magnitude without significantly affecting the crystal lattice. So that's why we can go for a doping. So already I told that according to the type, in extrinsic semiconductor, we can have that is can be subdivided into two categories. One is N-type extrinsic semiconductor, and another one is P-type extrinsic semiconductor. So in extrinsic N-type semiconductor, by adding a pentavalent doping element to that purest form of either silicon or titanium, we can able to produce N-type semiconductor. So it can be formed by adding group elements like phosphorus or arsenic. So that extra fifth electron, it has a five valence electron. So the four electrons are covalently bonded with the waveform of semiconductor. That extra fifth electron is loosely bound and becomes a majority carrier of negative charge. So here the majority has electrons and minority has holes. So that is nothing but n-type semiconductor. And the next type of instance is p-type semiconductor. So according to this type, we can able to add trivalent dopant to the purest form of the semiconductor. So it can be formed by adding group 3 elements like boron or aluminum. These have only three valence electrons, so that will create a vacancy or hole in the actual crystal structure. So this hole acts as a positive charge carrier. So according to this p-type semiconductor, majority has a holes and minority has electrons. So we can have a what is the main difference between the n type and p type according to the dopant type. In n type we can have a pentavalent impurity, in p type we can have a trivalent impurity. And impurity, based on the impurity, we can say in n type as a donor impurity and the p type except R impurity. So majority carriers in n type has electrons. So because of the pentavalent impurity, we can have a more number of electrons in that n type extrinsic semiconductor. According to the p type, we can have a holes as a positive charge carrier. So the majority has holes. So according to the Fermi energy level, the Fermi energy level E, which lies, which is near the conduction band, according to type, which lies near the valence band. So now we want to the expression for intrinsic carrier concentration. So first we need to discuss what is the definition for this intrinsic carrier concentration. It is nothing but number of charge carriers per unit volume. Okay. Charge carriers per unit volume is nothing but intrinsic carrier concentration. So now we need to concentrate only, we are concentrating intrinsic semiconductor ion. So according to the intrinsic semiconductor, we know that silicon is a best example for the intrinsic semiconductor, and also it has an equal number of electrons and holes. So according to this intrinsic semiconductor, the first we need to find out what will be the charge density of electrons and what will be the charge density of holes. Then after that only we can able to find out what would be the intrinsic carrier concentration. So, for example, if you want to find out density of electrons in conduction batteries, the number of electrons per unit volume. Same way, when we need to find out what will be the density of holes and the number of holes in valence band per unit volume. So, with that basis only, we can able to derive intrinsic carrier concentration. So, according to the structure, so we can take a very simple structure as a silicons. So, for example, if you take as a silicon means, so all the silicon atom, it has a four valence electrons. So all the four valence electrons, it can be covalently bonded with its nearest neighboring silicon atom. So it is a covalently bonded with its nearest neighboring. When you see the energy band structure, this is a conduction band. And in between the Fermi energy level, which lies in between the conducting band and valence band. And also, according to this intrinsic structure, the valence band is a completely filled structure. Filled structure. So at 0 Kelvin, at 0 Kelvin, so we can't able to create any free electrons. So when we increase the temperature as greater than 0 Kelvin, so what happens? There will be a breaking of covalent bond that's happening. So there will be a breaking of covalent bond. So you know what happens? So for example, if the bond is break, so there will be a creation of holes here. So then the electron can be moved somewhere else. So with that, we can able to create more number of free electrons, free electrons in the valence band. So then we can able to create an electron in the air conduction band. Free electrons in the air conduction band. So with that increasing free electrons, we can able to find out that is a charge density, or we can find as a number of electrons will be conduction band. So first we need to see the number of electrons will be conduction band as said increases from 0 to 1. Okay, so because of that increasing free electrons in the conduction band, so based on the same equal in number, so that will create holes in the valence band. So with that basis, we can able to derive what will be intrinsic carrier concentration. Okay. So in order to derive the intrinsic carrier concentration, first we need to derive the density of electrons in conduction band. So when we concentrate the conduction band, so this is the conduction band. So we can have the energy levels, it starts from Ec to infinity. So what we need to do is we need to find out density of electrons in conduction band. We can able to express as dn is equal to z of e dE into f of e. So this f of e is the probability of occupancy in that conduction band, and also this is the density of electrons in our conduction band. So as we know in general, so in order to find out the n, n is nothing but density of electrons in conduction band. So n is equal to, we can equal to get an integrator this dn. So integral of dn, that is equal to z of e dE into f of t. Okay. So we can able to fix the limit. We need to find out what will be the number of electrons per unit volume within limit or within the limit lies between is equal to infinity. So with that we can able to write this expression as Vc to infinity dn is equal to z of e dV, which is multiplied by f of t. So we can able to start with that expression as z. First we need to write what is this z of e. So this z of e is really already we have studied generally in conductors. So if we try by h2, which is multiplied by 2n star to the power 3 by 2. So according to this expression, the semi can be the mass of an electron. It is the effective mass of an electron. So that's why we can able to represent this 2m star to the power 3 by 2, and which is multiplied by 3 power half. So e power half into so this is the density of energy state. So with that, with this expression, so we can be replaced by v minus this. So we can change this expression as z of e dE is equal to 4 pi by h2, which is multiplied by 2n star to the power 3 by 2, which is multiplied by e minus ec to the power half into dE. So this is the z of e dE expression, and also we should know what is meant by f of e. F of e is the probability of occupancy in Fermi energy level. So as we know, the central expression as 1 by 1 plus e to the power e minus ef by kt. So since kt is very large, since kt is large, so the term e to the power e minus ef by kt is large as compared to this one. So we can neglect 1 in the denominator. So the expression can be written as f of e is equal to 1 divided by e to the power e minus ef by kt. So we can write a general expression as n is equal to integral of Pc to infinity z of e dE into f of e. So we can able to write 4 pi by h2, which is multiplied by 2m star to the power 3 by 2 into e minus ec to the power half into dE, which is multiplied by 1 divided by e to the power e minus ef by kt. So the next thing we need to take the constants outside. So only the variables which are used to do the integration. So we can able to write n is equal to 4 pi by h cube, which is multiplied by 2m n star to the power 3 by 2 integral of AC to infinity. Then we have an expression a minus AC to the power half is multiplied by 1 divided by e to the power 1 minus EF by KT. So first we need to move to this denominator into the numerator. So this term, the whole term is same, and then we can have AC to infinity e minus AC to the power half, which is multiplied by e to the power minus of e minus EF by KT. Okay, so the next step, as the first term is as same as it is, also AC to infinity e minus AC to the power half. Here we can have e to the power plus EF by KT. Then we have e to the power minus E by KT. So the same expression can be written as the first term as the same, and this e to the power minus EF by KT doesn't have a role with respect to this e. So that's why e to the power EF by KT, we can take it outside. So AC to infinity e minus AC to the power half, which is multiplied by, sorry, I'm using all the expressions with respect to e to the power minus m by KT into d. Okay, in order to simplify this integral, we can go for substitution method. So we can have an expression n is equal to 4 pi by h2, which is multiplied by 2m a star to the power 3 by 2 into e to the power kf by kt, integral of AC to infinity. And then here we have a u minus AC to the power half into e to the power minus 3 by kt into d. So in order to simplify the integral, we can have this AC minus E minus AC as x. Okay, so dv is equal to dx. So we need to substitute the limit as when we have when E is equal to EC, when E is equal to EC, so x is equal to 0. Same way, when E tends to infinity, E tends to infinity, we can substitute this E tends to infinity here. So what happens? Infinity minus EC is equal to x. So when E tends to infinity, x also tends to infinity. And also here we need to find what is E. So E is equal to AC plus x. So with this substitution, this is equal to AC plus x tends to 0 to infinity. So we can have integral, how can be changed? N is equal to and is equal to 4 pi by h cube, which is multiplied by 2m e star to the power 3 by 2, which is multiplied by 8 e to the power ef by kt, and interval the limit has changed 0 to infinity, e minus ec as x to the power half, and e to the power minus ec plus x by kt into dx. So with that expression, e to the power minus ec by kt is not dependent on the x. That's why we can take it outside. So 4 pi by h cube, which is multiplied by 2 e star to the power 3 by 2 into e to the power ef minus ec by kt. So we can have an integral 0 to infinity x power half and e to the power minus x by kt into dx. So with the help of gamma function, you can able to solve this. That is x power half integral 0 to infinity x power half into e power minus x by kt can be written as into dx can be written as kt to the power and 3 by 2 into 5 by 2. So we can substitute with that above expression n is equal to 4 pi by h cube, which is multiplied by 2n of 3 by 2 into e to the power ef minus plus ef minus by kt, which is multiplied by kt to the power 3 by 2 into pi to the power by. So we can evaluate on this one plus 2, and also here we have pi to the power 1. Here we have a pi to the power 1, here we have a pi to the power half. Here also we can have a 3 by 2. To the power 3 by 2. So we can able to combine these two terms. So that's why 2 pi power half 2m e star to the power 3 by 2 q3 to the power 3 by 2 by h cube. Pi power half plus 1. So that's why pi power 3 by 2 h. And also here we have ef minus ac by kt. Okay. So we can combine all the terms 2 which is multiplied by 2m by pi power half and then kt power 3 by 2. Finally we can combine all the terms because all the powers are 3 by 2. Then 2 which is multiplied by 2 pi m e star kt, and also we can able to write this h cube as h square to the power 4 to the power 3 by 2, which is multiplied by e to the power 3f minus ac by k into t. So this is the expression for density of electrons in conduction band. Same way, you can able to find out what will be the density of holes in the valence band. Same way, we can able to find out the density of holes in the valence band. So that can be represented as the density of force can be represented as dP, that is equal to Z of E dE, which is multiplied by 1 minus F of E. So the F of E is the probability of occupancy as an electrons generally. So already we derived F of E for density of electrons in the conduction band. So the total probability is 1. So if we have 1 minus F of E, then we can able to get easily probability occupancy of holes in valence band. So according to this valence band, so the maximum energy level as represented by the letter EV. So and also here we have a name as minus infinity. So with that minus infinity to EV, what would be the number of holes which is present at energy level in between minus infinity and that can be derived here. So in order to find out the number of EV, so we can have minus infinity to EV, that is E, which is multiplied by Z of E dE into 1 minus F of E. Okay, so this is the basic expression. First we need to know what is this Z of E dE. So same way here we can have 4 pi by H2. Here 2m H star. Here we are concentrating those. So that's why the effective mass of the pole can be introduced here. 2m H star to the power 3 by 2, which is multiplied by 3 to the power half into d. So instead of this 3 by 4, we can find out what is the difference in EV minus E. So E can be replaced by EV minus E. So 4 pi by H cube, which is multiplied by 2m H star to the power 3 by 2. It can be replaced by EV minus E to the power half into. So next we need to know what is F of E. So this F of E here according to this case, F of E is 1 minus F of E. So 1 minus 1 divided by 1 plus e to the power e minus EF by KT. So we need to take LCM. So for that we can equal to write 1 minus F of E can be written as 1 plus e to the power e minus EF by KT minus 1 everything divided by e to the power e minus EF by KT. So with this expression, we can be able to cut this 1 and 1. And also we can introduce, since this E is large as compared to this E. So E is large because of this e to the power E is large as compared to this EF. So this e to the power e minus EF by KT is negative. So because of e to the power e minus EF by KT is negative, just very low value as compared to this one. So we can neglect this low value. That is the second term in the denominator, e to the power e minus EF by KT. So we can have only 1 in the denominator. So we can simply written as 1 minus F of E is equal to e to the power e minus EF by KT. So we can substitute that 1 minus f of to that the general expression as P is equal to integral minus infinity to EV, which is multiplied by 4 pi by h cube, which is multiplied by 2m h star to the power 3 by 2, which is multiplied by EV minus E to the power half into dV, which is multiplied by e to the power e minus EF by K. So in order to simplify this, we need to take out the constants. So P is equal to 4 pi by h cube, which is multiplied by 2m h star to the power 3 by 2, which is multiplied by integral minus infinity to EV minus E to the power half into dE, which is multiplied by e to the power e minus EF by KT. Same way, we can introduce a substitution method as select EV and also Abhilash, Abhilash. When the PPT, so with that continuation of density of holes, P is equal to P is equal to 4 pi by h cube, which is multiplied by 2m h star to the power 3 by 2 into e to the power EV minus EF by KT. So in order to change in order to use that a negative sign of the dx, we can able to change the limit as 0 to infinity x power half into e to the power minus x by kt into dx. So in order to solve with the help of this gamma function, we can able to simplify this x power half into e power minus x by kt into dx is equal to pi to the power half into kt to the power 3 by 2 by 2. So we can substitute this value to that above expression. So we can return as P is equal to 4 pi by h cube, which is multiplied by 2m h star to the power 3 by 2 into e to the power EV minus EF by KT, which is multiplied by pi to the power half into KT to the power 3 by 2 by. Same way, this 2 and 2 we can simplify. So same as for the case of any type, we can combine this pi to the power 1 and pi to the power half kt to the power 3 by 2. So we can simplify this 2 and 2 pi mh star kt and also we can have h square to the power 3 by 2, which is multiplied by e to the power EV minus EF by k. So this is the final expression for P. So we can write like this: 2 which is multiplied by 2 pi mh star kt by h square to the power 3 by 2, which is multiplied by e to the power ev minus ev by n. So with that basis, easily we can able to derive what will be the intrinsic carrier concentration with the help of the term N and P. So now we are going to derive intrinsic carrier concentration. So as I have already derived density of electrons in the conduction band and density of holes in the valence band. So density of electrons in conduction band. So as already we derived, N is equal to 2, just multiplied by 2 pi ma star kt by h square over power 3 by 2, which is multiplied by ef minus ec by kt. And also we know that density of holes in valence band. Okay. P is equal, that is represented by delta P, that is equal to 2, which is multiplied by 2 pi mh star kt by h square to the power 3 by 2, which is multiplied by p to the power ev minus ef by kt. So these two are already derived. And in order to find out the intrinsic carrier concentration, as we know already, in intrinsic semiconductor, the number of or the density of electrons in conduction band is equal to density of holes in the valence band. So we know that N is equal to P. So with that concept, we can introduce Ni squared is equal to N into P. So if we need to multiply these two expressions, easily we can able to find out what will be the intrinsic carrier concentration. So for that, I need to multiply these two expressions. So N squared is equal to, that is N into P, 2 which is multiplied by 2 pi m star kt by h squared to the power 3 by 2, which is multiplied by e to the power df minus ec by kt into 2, which is multiplied by 2 pi m h star kt by h square to the power 3 by 2 into e to the power ev minus ef by kt. So according to this expression, usually we can able to multiply this 2 into 2, and also according to the second term, 2 pi kt by h squared is common for both the term, and the remaining me star to the power 3 by 2 is different because this is the effective mass of an electron. This is the effective mass of a hole. The two terms are different terms, and also according to this e to the power. So when you multiply these two terms, we can able to add the exponential terms. Simply we can have e power ev minus ec by kt. So with that 4, which is multiplied by, when you multiply these two, 2 by kt by h square, so we can have only to the rest of 3 alone, and the remaining terms m star to the power 3 by 2, and also m star to the power 3 by 2, and mh star to the power 3 by 2, which is multiplied by e to the power ev minus ec by kt. But according to the left hand side, we can have a Ni squared. So in order to take a square root on both sides, Ni is equal to 2, which is multiplied by 2 pi kt by h square to the power 3 by 2 into mv star to the power 3 by 4, which is multiplied by mh star to the power 3 by 4 into. So generally the difference in energy level between this valence and conduction band. So this is Vg by 2kT. So this is the final expression for intrinsic carrier concentration. So we can derive at last, we can derive so this is the final expression for intrinsic carrier concentration that is represented by the letter N. So even if we arrive at the intrinsic carrier concentration, we should know the energy, Fermi energy level of intrinsic semiconductor, because that is very important. With that only we can able to get the number of electrons in conduction band and number of holes in the valence band. So next we move on to the effect of the Fermi level based on the temperature. So simply we can write Fermi energy level based on temperature. So what is meant by Fermi energy level? Fermi energy level is a characteristics energy level. Fermi energy level is a characteristic energy level. So with the help of based on the value of EF, based on the value of EF only, we can decide the number of electrons in conduction band and number of electrons in valence band. So that's why this Fermi energy level is very important term in the semiconductor. Okay. So as we know already, we know that in intrinsic semiconductor, so we can have N is equal to P. So what is this N is equal to P? Number of electrons in conduction band, that is equal to number of holes in valence band. So with that basis, easily we can able to get what is the value of F. So I have to introduce N is equal to P. So what is N? 2, which is multiplied by 2 pi M star kt by h square to the power 3 by 2, which is multiplied by e to the power EF minus EC by kt. That is equal to 2, which is multiplied by 2 pi m h star kt by h square to the power 3 by 2 into e to the power EV minus EC by EF. EV minus EF. EV minus EF by KT. So when you compare these two terms, we can able to cancel out this 2 and 2. And also we can have 2 pi kt by h square to the power 3 by 2 is common for both the term. Then we can have remaining terms as here we have m e star to the power 3 by 2, which is multiplied by e to the power pf minus dc by kt, that is equal to m h star to the power 3 by 2 into e to the power ev minus ef by kt. So what we need to do, we need to find out what is the value of ef. So what I can do is e to the power ef minus dc by kt, that is equal to m h star to the power 3 by 2 divided by m v star to the power 3 by 2 into e to the power ev minus ef by kt. So what we need to do in order to find out the value of ef, taking log on both sides. Taking log on both sides. Here what happens? ef minus dc by kt, that is equal to, what happened here is 3 by 2 log of mh star by me star plus ev minus ef by kt. So we can rearrange these terms. So what is that expression? So according to this slide, we can have a term ef minus ec by kt, that is equal to 3 by 2 log of mh star by me star plus, because we are taking log on both sides, you know. So ev minus ef by kt. And also the next step is I want this ev minus ef by kt to left hand side. So that's why here we have a plus term, and so here I put minus term, minus of, actually minus of ev minus ef by kt, that is equal to 3 by 2 log of mh star by mh star. So the denominator is same for both the terms. Here denominator is also going to be equal. Then this minus multiply this minus over here. So what happened? Minus EV plus EF. So that's why when you simplify the numerator, 2 EF minus EC minus EV by KT. So that is equal to 3 by 2 log of MH star by ME star. Okay. So, and also I can split into two terms here, in left hand side, 2 EF by KT earlier, and also minus of minus EC minus EV by KT is the second term. So that second term I move to the right hand side. So that's why all the negative terms are also plus. So EC plus EV by KT plus 3 by 2 log of MH star by MH star. So now I simplify this term. So because I need to find out what is this EF. Okay. So based on this EF, I can, what can I do is multiply KT by 2 for both the terms in right hand side. So that's why I can rewrite this. EF is equal to EC plus EV by 2 plus 3 by 2 KT log of MH star by MH star. According to this term here, we can have 3 by 4 KT. This is the expression for Fermi energy level in intrinsic semiconductor. So even though if we know the value, then what happens? What will be the variation of energy level with respect to temperature? we have the temperature and here we have a value of Vx. Okay, so this is the conduction band. Effect of temperature on sound. Variation of temperature with respect to energy. Okay, so this is the conduction band and this is the valence. Okay, so here we have some electrons is present in conduction. So as temperature or at the temperature at 0 Kelvin, so what happens when mh star is equal to me star? So what happens the EF, the second term, as we are having the log value, log of mh star by me star. So when you substitute over here, so if it is the both are equal, then what happens? It is a log of 1. So we are getting the value as 0. So as the equation in EF, the second term is 0. So only we are having EF is equal to, so EC plus PV by 2. So it lies midway between the Fermi energy level lies midway between valence band and conduction band. So that's why we can able to draw the Fermi energy level like this. So this is the EF. So this is the condition for at 0 Kelvin. So if you raise the temperature, or at here we can have a T is equal to 0 Kelvin. But now we can change the T is equal to or T greater than or equal to 0 Kelvin. So this Fermi energy level just shift above the actual energy level. So as the temperature increases, it shifts towards the conduction band. So even so, it is not a simple case as we increase the temperature, we can have a energy level that is shifted towards the conduction band. And next we need to see, even if you find out the value as generally simply we can say the energy level, Fermi energy level, it shifted above the actual energy level. But we have some limitations in intrinsic semiconductor. The limitations in limitations on intrinsic semiconductor. So what are the limitations is? So we know that at 0 Kelvin, the Fermi energy level lies between conduction band and valence band. So in order to increase the temperature, we can have some Fermi energy level. But according to when you are concentrating the conductivity or the electrical conductivity of intrinsic, so what happens is we can have only very low value. So even if you increase the temperature or even if you increase the temperature or by increasing the electric field, so there are two ways to achieve this, achieve to enhance the electrical conductivity. Even if we increase the electric field, we can't able to increase the electrical conductivity of the intrinsic semiconductor. It is simply 10 power 7 times low as compared to metals. As compared to metals. So easily we can't able to increase the electrical conductivity. That's why we need to introduce the doping concept. In order to increase electrical conductivity, we need to introduce doping.